Okay, so let's consider a thin flat plate at a 5-degree angle of attack. Now with that, we want to calculate the lift coefficient, the moment coefficient about the leading edge, the moment coefficient about the quarter chord point, and the moment coefficient about the trailing edge. So now what's kind of cool is we can relate the thin flat plate to a thin symmetric airfoil. So we can actually use the equations for our thin symmetric airfoil for lift coefficient and our moment coefficients for this thin flat plate. So you can imagine a very thin rectangle extruded either in or out of the page. And so it's going to be symmetric in our y dimension. So we can essentially use these relations to solve this problem. So let's get started. So for part A, we'll be solving the lift coefficient. So for a thin symmetric airfoil, lift coefficient is equal to 2 pi times alpha. So essentially I have 2 pi times 5 degrees. But with this, we actually want to convert that into radians. And the reason we want to convert this into radians is so we don't have that extra degree term there floating about. And now another reason that we convert this into radians is notice if we multiply this out, we would get 10 pi, which is essentially greater than 30. So that'd be a very significant coefficient of lift for a wing, which would be a very great plane, but that'd also be an indication that something might be slightly off because it's a very, very high lift coefficient. But anyways, so we'll essentially take our alpha and then convert that into radians. So that'll give us a coefficient of lift equal to 0.5485. Okay, so for part B, what we will be doing is we will then be calculating the moment coefficient about the leading edge. So we'll have C sub m, gamma, L, E. So coefficient of moment about the leading edge. Now this is defined as the coefficient of lift divided by 4, or the negative coefficient of lift divided by 4. So then we'll essentially have negative 0.5485 divided by 4. So we'll have CMLE is equal to negative 0.137. Already 2 parts done. Look at that. 2 more to go. So for part C, we'll calculate the coefficient of moment about the quarter chord point. So essentially CM comma C divided by 4, because we're taking essentially 1/4 of our chord. So this will be equal to CMLE, or the coefficient of moment about the leading edge, plus coefficient of lift divided by 4. Well, in this case, this will actually equal 0. And in fact, for all thin symmetric airfoils, this will equal 0, which is kind of cool. It's a neat little, I guess, property to definitely remember later on for especially designing airfoils. Hint, hint. Okay, so for part D, last part. So we have a little drawing down here, so I'll move that up. And this is essentially of the thin flat plate. So you have your very thin flat rectangular plate here. You have your tailing edge, and then this will be your leading edge. We have a 5-degree angle of attack at some free stream velocity acting upon it. Now, at the tailing edge here, we have this moment arm A. And now we can define that moment arm A as being equal to 3c divided by 4, or essentially 3/4 of our chord length, times cosine of 5 degrees. Now, for thin airfoils, we actually assume that alpha is significantly less than 1, such that cosine of theta is equal to 1, or I should probably write it's approximately equal to 1. So then, with this in mind, we can actually write that our moment arm A is equal to 3c divided by 4. So now we can, keep on solving the problem. So the moment, or I guess the moment per unit span of the tailing edge, that is going to be equal to our essentially moment arm A here, 3c divided by 4, times the essentially lift per unit span, because our lift is going to be perpendicular here in this case. And then we are adding the moment about our quarter chord. So essentially m prime c divided by 4. So what we can then do is we can actually divide the entire equation by q infinity c squared, such that we just get down to our coefficients. So we'll have cm te, or the coefficient of moment about the trailing edge, and that'll be equal to, so I have m prime te divided by q infinity c squared. So essentially I have 3/4 c, and then L prime divided by q infinity c squared, and then plus m prime c4 divided by q infinity c squared. So then that will leave us with, let's see, so we'll have our 3/4, that's not going away, and then we'll have the L prime divided by q infinity c squared. Well, we know that L prime is equal to q infinity CL times C, where CL is our coefficient of lift, q infinity is our dynamic pressure, and then C is our chord length. So essentially, if we divide by our q infinity times c squared, we'll be left with a factor of c here in the denominator, but that'll just cancel with that c. So we're left with 3/4 CL. And then we have plus Cm of our chord, which we said from before, that's just equal to 0. So now all we have to do is plug in CL. So we have 3/4 times CL, which is 0.5485, and we get a coefficient of moment about the trailing edge equal to 0.411.